everyone. I'm Disha Puri. I lead the datapath formal verification team at Intel Graphics. Intel Graphics is teaming with algorithms such as integer and floating point operations, address translations, image enhancements, compression, decompression, etc., which, if can be completely verified with formal, can bring a lot of value add and shift left to the verification cycle. This talk is about some of the challenges that we have faced and how we have resolved it. I'm presenting on behalf of the co-authors Kiran, Mohit, and Paras. So this is the agenda for today. First, we will build some background on the introduction to datapath formal verification, and I'll discuss some of the challenges that we have faced. Then we will look at the solutions in the form of two case studies. In the first case study, we have been able to manage datapath formal verification without even having a specification model. In the second, we discuss some of the convergence techniques we used in one of the very complex designs we dealt with in graphics. I'll then summarize with a wrap-up slide. So first we talk about what exactly is datapath formal verification. Datapath designs are those designs that deal with data transformation or manipulation. For example, all of the arithmetic designs like integer and floating point operations, shift operations, they all fall under the category of data manipulation. There could be algorithmic designs such as data compression, decompression, error correction codes, address translation, tiling algorithms, media enhancement algorithms. All these designs fall under the category of arithmetic designs, which are called datapath designs. This slide represents how traditional datapath formal verification is done in the industry so far. So we have a reference model, the specification model in the left-hand side, which we consider golden. It could be a C, C++ or a system C high-level model, or it could be a Verilog model which is more straightforward than the implementation. On the right-hand side, we have the implementation model, which is usually the system Verilog model, which we are trying to validate. We do an input-output equivalence between the two models, which is that we assume that both of them have the same symbolic inputs, and in the end we verify that they eventually give out the same outputs at the end of the transaction. One thing to note is that they may not be same in terms of the cycles they consume. So for example, the C or C++ or system C could actually be untimed, while the system Verilog models will take multiple cycles to complete the transaction. However, in the end, we want to verify that the outputs from both the designs are indeed equal for all possible inputs. If we are able to converge on that assertion, then we would be able to claim that two models indeed behave the same way algorithmically. However, this traditional formal verification comes with its own set of challenges. The first challenge is perhaps obvious but very important, which is the availability of a golden C++ reference model. All the designers and RTL validators may not have the liberty of having a golden high-level reference model. Even when a C++ model is available, it may not be written with formal consumption in mind, and tool may not be able to use that model without a lot of changes. At Intel Graphics, C++ models are tuned for performance and use lot of dynamic constructs, STLs, and legacy libraries for correctness and efficiency purposes, which itself poses a challenge for a formal tool. Second challenge is to be able to map the boundary of an algorithm between C++ and RTL and define a constrained environment for it. A classic example is that when an RTL designer writes a compression-decompression design, valid inputs at decompression are those which are coming from compression algorithm. However, for formal validation, decompression is a standalone algorithm and we need clear understanding of valid inputs at that boundary. Another common challenge across industry is that the designs are becoming increasingly complex to meet the market competitiveness, not only in terms of efficient algorithms, but also to save power, area, etc., which poses a huge challenge for the verification community. We will now discuss two case studies to share some of our important learnings with the verification community. The first is about the kind of problems which can be verified formally even without a C++ model. Graphics pipeline needs an execution unit for various integer and floating point operations, as I mentioned earlier. It handles the arithmetic operations and is referred by various algorithms multiple times, which makes the correctness of this module extremely critical. Formal verifies a major chunk of this using standard high-level model versus RTL methodology. However, recently, a residue block was added to this unit for additional safety and detect functional errors. The residue block is more like an error correction code, which calculates mod of inputs, does the same operation as the normal pipe, and then compares the output with the mod of the output as expected from the residue pipe. It is supposed to give an error signal in case of mismatch. The time to market constraints required immediate validation help, and there was no C++ model for this particular block and no time to bring it up. Formal was asked to help. Control path is known for formal property verification, but we decided to try FPV for data path for this particular block. As a first step, we validated the normal execution unit using our standard SLM to RTL methodology. Then to validate the residue block, we wrote a property on the error output that the error output is never asserted. It was a huge verification problem with a large data set and about 40 opcodes, both integers and floats. Imagine having to validate a complete set of double precision inputs for an algorithm. With data path property verification, we used multiple techniques like assume guarantee and case splitting to solve the problem, and we found around 20 issues in a very small time frame, even though simulation would have been running for quite some time. Using property verification and just one assert on every opcode, we were able to prove this big data set in a very small amount of time with a huge ROI. The second case study is on how we converged on a big design, parallel dot product accumulate, which is used in matrix multiplication and is very essential for machine learning algorithms. It's a huge design which basically does multiply and accumulate repeatedly across multiple stages. It allows all sorts of formats, integers, half floats, B floats, various custom floats, and does not comply with IEEE standards. As you can imagine, formal is extremely important for such algorithms, as you cannot possibly cover all vectors in simulation environment, and chances of corner case bugs lurking are very, very huge. The first challenge we faced was that C++ code was built on Intel's legacy floating point customizable libraries, which were formal, non-formal friendly. They were constructs which were not supported by the formal tool. So we replaced some standard functions with pre-verified formal friendly code and open source libraries to tackle that problem. The other problem that we faced that there was an intermediate 256-bit vector to store the intermediate mantissa result, which was not supported by the formal tool. The way we handled this problem is that we replaced it with 64-bit vectors based on the understanding of precisions and rewrote a certain portion of C++ code so that FP tool can handle that complexity. Another obvious problem is that it's a huge design with multiple stages of pipeline. So we cannot possibly verify it with an end-to-end verification. We use divide and conquer to first map a single C++ stage with RTL, and then we use the proof from the above step to prove further stages. There was another problem is that there were a lot of bypass cases which were not following this single stage streamlined approach. So we had to figure out those bypass cases on conditions like nan infinity 0, and then figure out those flags which we were supposed to map for those particular C++ and RTL values. Then we need to infer the mappings based on the understanding of these bypass cases, which ended up with multiple complex properties. This slide represents the divide and conquer approach, which became the linchpin of this particular verification problem. So we first would solve one particular stage. The plus over here represents the 4 multiplications going on in that particular stage. We verified the stage 0 output of C++ against the RTL, and we verified the stage 1, which was taking the input from the previous accumulated result as another stage. So every stage we would treat as a separate individual entity and use the divide and conquer approach to solve this problem. Like I mentioned earlier, for bypass cases, this approach does not work. So they needed to be figured out separately by using a bypass case across the entire stages, all the particular stages at once. Formal was up on this design after simulation had been running for a very long time. The reason being because the setup was huge, it took a lot of time for Formal to bring up. But even after that, we found 2 corner case bugs on this design, which were considered to be showstoppers. And for every future generation, once this was up and running the first time, we were able to use this RTL as golden and quickly verify the next generation RTL and find bugs with a huge shift left even before the simulation was up and running. This slide basically describes one of the corner case bug that we found through this verification. The design issue was that the RTL was not able to detect correctly whether the accumulator input for float is denormal or not. Because if the input was denormal, it needed to be flushed to 0. So it basically shows in the left-hand side column what was the RTL equation, which was incorrect equation given in the RTL, and what is the correct equation should have been. The reason that this was a corner case bug was that this bug was only found in the case which is given in the second column, where the exponent was 0 and the mantissa were all ones. Only in that particular case, RTL was setting the denormal flag incorrectly. Otherwise, in all the other cases, it was absolutely correct. It was leading to a potential mismatch in output, which was equal to the value of the least significant position mantissa bit of the final output, leading to a bug. In simulation, this bug was not found, even though it had been running for quite some time. However, in Formal, we wrote a simple assertion between the C output and the RTL output at stage 0, and we were able to quickly find this corner case example. The simple assertion said that for cases when it is a non-bypass case, that is, both the inputs source 1 and source 2 are neither nan nor infinity, which means that we are not going through the multiplication stage. In that case as well, the output of C++ should match with the output of the RTL for that particular stage. With this simple assertion, we were able to find quickly this particular corner case in which the bug was there. Now to summarize, Datapath designs usually have a huge data set and they need to specialized tools to be verified formally. Traditional datapath formal verification requires a C++ code that is consumable. It functionally matches the intent of RTL and has an interface that can be mapped with the RTL. However, we figured out a way of using property verification through datapath tools which can be utilized successfully even if C++ code is not available. And also, by handling complexity intelligently, we were able to handle complex designs with good convergence, complete convergence, and find corner case bugs. And we were able to leverage the RTL to RTL technology for future generations once we were able to goldenize the first generation. Thank you.